Hey everyone, welcome back to another ChemiVid. Today we'll be talking about mole and mass fractions. So if you remember all the way back to the engineering units video, I mentioned them, but today I wanted to go a little bit more in depth as to what they are because they're so important to chemical engineering. So let's start with a mass fraction. You can see here I have it denoted x sub I, so that just means the mass fraction of component I. It's in a mixture. And really the way it's defined is quite simple. It is the mass of I over the mass of the mixture. Quite simple, but very useful. Now the same goes for mole. I have it denoted x sub I. I have it distinguished by telling you that it is a mole. This is the case with all mole and mass fractions. They have to tell you whether it is a mass fraction or whether it is a mole fraction because they're inherently different. So x sub I on a mole basis is the moles of I divided by the moles of total mixture. Okay, so I'll add that right here, the mass of total mixture. That's important that it is everything, including species I. Just a little review from chemistry here. If I go to a certain element, like maybe carbon, I can see its atomic weight is what they call it, 12.011. To a chemical engineer, really what we do when we see that is we say, okay, it's 12.011 grams per mole. And that's how we relate grams, a weight or a mass, to moles, which is an amount of chemical species. Just to note, 12.011 grams per mole equals the same as 12.011 kilograms per kilomole. Remember those units. And that's also the same as pound mass per pound mole. So the important thing about these units is that the top mass unit matches the bottom moles unit. So if it's a pound mass, it's a pound mole. Let's do an example. I think it will become a little more concrete as we do this example. So let's say I have a mixture of components A, B, and C. So I just have some tank, let's say, and I have components A, B, and C all mixed in together. I know I have 300 kilograms of A, 200 kilograms of B, and 500 kilograms of C. What is the mass fraction of A? Well, if we go back to our definition right here, it's the mass of, in this case, A over the mass of total mixture. So let's write it out symbolically. We have the mass fraction of A will be equal to the mass of A over the mass of the total mixture, which is mass of A plus mass of B plus the mass of C. So that will be 300 kilograms. And if I sum all these up, I will get 1,000 kilograms. So the mass fraction of A in the mixture is 0.30. Very simple, and it's the same with moles. Really, the tricky part comes when you have a mass fraction, but you need a mole fraction, or vice versa. So let's talk about what you do to handle that. Let's say I have a mixture of O2 and N2, so basically air, and the mole fraction of oxygen, I've denoted it with a Y here. X and Y are very common. You may see Z as well as you get into distillation. But I have a mole fraction of O2 of 0.21. So what is the mass fraction of O2 in that mixture? This can get a little confusing, but it's actually very simple. So what we do is we say, all right, let's assume a basis. Let's say I have 100 moles of this mixture of O2 and N2. Well, let's go to the definition of, we want a mass fraction, right? So let's go to the definition of that mass fraction. It's going to be the mass fraction of O2. I'll denote it with an X this time. And I know that's going to be the mass of O2 in a mixture over the total mass of the mixture. So the mass of O2, well, okay, I'm doing it based on moles. So I know in this mixture of 100 moles, I have 21 of those moles of O2, right? And I know that down here I have 21 moles of O2. I'll be adding to that the 79 moles of N2, but notice this is moles over moles. That's still a mole fraction, so I need to convert these, and this is where the periodic table comes to, because we know on the periodic table that a mole of O2 is 32 grams. So I can come do that conversion here. Mole of O2 is 32 grams, and a mole of N2 is 28 grams. Now the moles cancel everywhere, and we're left with a grams divided by grams. So if you do that calculation out, you will get that the mole fraction of, the mass fraction of O2 is 0.233. Now notice how the mole fraction of O2, right, and I'll do this just for comparison, was smaller than the mass fraction. That's because oxygen in that mixture actually weighs more, it has more mass than nitrogen does, and so we expect it to have a higher mass fraction as opposed to a mole fraction. Pretty cool, huh? So continuing on, let's do another example, but we're going to go the other way. We have mass fractions or weight fractions, and we want to get mole fractions. So looking here, we have a mixture of methanol and acetone. And we want to figure out that if I have a mass fraction of methanol of 0.4, what is the mole fraction? So we're going to do the same thing. We're going to assume a basis of 100 grams this time instead of moles. And we know that the definition of a mole fraction, CH3OH, is equal to moles of CH3OH divided by total moles. So we know if we have 100 grams, 40 of those grams are CH3OH, and 60 of those grams then must be acetone. So what we can do is, I have right here written the molecular weights. I can say that 22 grams is a mole of methanol, and do the same thing here. And then add that to the 60 grams where 58 grams is a mole of acetone. And now I have moles divided by moles, so the mole fraction, when you calculate that out, is 0.637. And there we go. There is our answer. So it's really easy. The process is assume a basis of whatever unit you're given. So if you're given a weight fraction or a mass fraction, assume a basis of mass. If you're given a mole fraction and need a mass fraction, assume a basis of moles. And then continue on with the conversions you can get simply from the periodic table. So quickly, before we end, I want to go over two really important properties. Let's say I have a mixture of n items, and x sub I denotes the mass or mole fraction of species I. Then the sum from the first species all the way to the nth species of x sub I, of the mass or mole fraction, is equal to 1. You're going to use this identity a lot in your engineering calculations, so it's something to remember. The other thing is units on mass and mole fractions. So technically they are unitless. And it's useful to think them as unitless because you have moles divided by moles or mass divided by mass. But there are times where it will be convenient to think of a mass fraction as mass of component I over total mass, and a mole fraction as moles of I over total moles. You get to decide what way you want to think about them. They're both correct, but it'll be easier to think about it in terms of these little units I've written here sometimes, and other times where it's a lot more convenient to just consider them unitless. So that's it for today. I hope you understand a little bit more about mole and mass fractions.